Okay, today we are beginning our new section on exponential models, Chapter 10. So the first thing we're going to do is we're going to do a little bit of an investigation using technology and some different functions. So let's type in some of these functions here and just see what happens. Okay, so my first function is 2 to the power of x, and then I hit graph, and we can see it has this type of a shape. And my next function is 1.5 to the power of x. And I'm going to graph both of them on the same axis, and you can see that this one has a similar shape. And if it goes from small up to bigger, you can see that this is going to be a growth. This is increasing as x gets bigger. So so basically our graph looks like this. Now something that's going to be very helpful is to look at a table to plot some points to draw our graph. So if I hit second graph, that allows us to get a table. So my first function, at 0, it crosses here at 1. And at -1, it's at 0.5. And at -2, it's at 0.25. At when x is 1, our value is 2. When x is 2, our value is 4. When x is 3, our value is 8. And you can see that it's growing exponentially. Now with our other function, when x is -2, we're at 0.4. That's somewhere around there. When x is -1, we're at 0.6. That's somewhere around there. When x is 0, we're at 1. Notice this is the same spot as the other graph. That's very important to notice. And then let's see, when x is 1, we're at 1.5. And when x is 2, we're at 2.5. So it's growing, just not quite as fast. Okay, and during class I saw people doing their drawings, and the most important key feature of these exponential graph is the y-intercept and the direction of the graph. So as you can see, this is increasing, and let's just graph another one for example. So here I've got 0.5, so I got 0.5 to the power of x, and if I hit graph, you can see that as x gets bigger, it decreases in value. So second graph gets us a table. So at -2, we're at 4. At -3, we are at 8. At -1, we're at 2. When we're at 0, we're at 1. And when we're at 1, we're at 0.5. And so you can see that this graph is decreasing in value. But notice here that when it crosses the y-axis, the y-intercept, it's also the same as these here. And we're going to see some characteristics that show this. So if I graph all of these, we end up seeing this kind of characteristic. You may want to hit pause. You should try to do this first before just copying this down. Now notice here, when I have 1 to the power of x, it doesn't matter what the power is, we're going to end up with a flat line. So, so one of the things you'll notice is whenever the base value is greater than 1, it's going to be an increasing graph, like you see in questions A, B, and E. And in questions C and D, notice when our base is here is less than 1, it's going to be decreasing. So as I said before, here my base is greater than 1, So it's increasing. Okay. And when it's less than 1, it's decreasing. And you can't have a negative base, because then you would have, uh, and we can talk about that later. So, so now it says, uh, what is the function? The function e to the x gives you, if what value gives f of x equal to e? Well, anything to the 1 value gets you the value of the base, right? So if let's type in this function, e to the power of x, and if I get my table, you can see when x is 0, we're at 1, and when x is 1, we have 2.7183, and that's about where I put this red dot here, and then we gave you the answer here. But anyways, the important thing was that you were able to type in the equation and hit second graph to get our table to see our relationship during our investigation. Okay, so before you just simply copy these answers, it's very important that you try to answer these questions on your own, and then check your answers. And let's read these questions. Okay, how can you tell from its equation whether the function is increasing or decreasing? Which of these graphs that you drew could represent cooling temperature? Which could represent growth? Which type of exponential equation represents growth and which one decay? You may want to hit pause to think about these. Okay, so so how can you tell if the equation is an exponential equation? It's going to be in this sort of form where the variable is in the power. Okay, and when a is greater than 0, it's increasing. We just talked about this a few minutes ago. Okay, so on the graph on the previous page, C and D could be cooling. Graphs A and B could be bacteria growth. Cooling means it's going to be decreasing in value. So an increasing graph shows growth, and a decreasing graph shows decay. Okay, so so construct a table and put these values in, and let's see what happens. So one of the things you're going to notice, so if I do 2 to the power of negative x, looks like that. I'm going to hit enter on this equal sign. That keeps it from drawing that graph. And now I do 1/2 to the power of x. And you're going to notice the graphs are truly identical. And if I hit enter over this equal sign, it's going to draw both graphs. And I only see one graph here. And now let's look at our table to see the values. And you're going to notice all the values are the same. Okay, so if I want to fill out the table here, you can go here to -3, and it's going to be 8. -2, it's going to be 4. -1, it's going to be 2. And you can see I've already filled out the table, and I've already drawn the graph. So it's important to use the table to get points to be able to draw a sketch of our graph. And as I mentioned before, when x is 0, the y-intercept is 1. Our y-intercept is one of the important points that we're going to be talking throughout this whole lesson. So explain why this to the negative x power is the same as 1/2 to the x power. And so the important thing to remember is that whenever you have a negative exponent, that means you have to take the reciprocal power in order to make the power positive. So here, to make this a positive x power, I have to take the reciprocal of this, which the reciprocal of 2 is 1/2. Okay, next page. Okay, now we're going to do an investigation with a more complex formula. So we've got the function. Whoa. We've got the function f of x equals 65 to this power. So I'm going to type this into my calculator, and let's do that right now. So we get 65 times 1.9 to the power of x plus 20. Now let's think about this for a second. Our base is greater than 1. But look, I've got a negative power to the x. So is this going to be growth or decay? You may want to hit pause and think about this for a second. Okay, before I give you the answer, let's see our graph and see if your hunch is correct. Notice, oh, first of all, you can't see anything here, right? So when you see something like this, you're going to need to adjust the graph. And I've given you a hint here that we need to change the Ymax value to 100. So how do I change the Ymax value? Well, if you hit Window, then we have these values here, and I can change the Ymax value to 100. And now I can hit Graph again, and there we go. There's my graph. And oh, this didn't come out the way I wanted to, and I see why. What did I do wrong here? Negative x power. I did not put a negative x power here. So if I go here to y equals, okay, so I want to insert a little negative power. You can do second delete, and notice it says ins. We're going to insert a negative power. So then I go second graph. Sorry, I go graph. And now the graph is going to look the way that you think it should work, because this is a cup of coffee modeling, right? Is coffee going to get hotter or colder? Think about it for a second. The temperature is going to go down. So, and as we learned on the previous example, on the previous page, whenever we have a negative power, we have to take the reciprocal of this. So normally, if our base is greater than 1, it would be growth. But because of our negative power, we're taking our reciprocal. And now I've got a fraction that is less than 1, and so this makes it decay, as we discovered when we did this problem. So here we're going to have decay, and we've got our graph here, and I've already pre-drawn it here, and you can see that it goes like this. Now the most interesting parts of this graph are the y-intercept and this line here. We're going to talk about this in just a second. So to get the y-intercept, I'm going to look at the table, and when x is 0, it's 85. Okay, so I've put a note here at 85. So why is it 85? And looking at this equation, how could we figure out where the 85 comes from? So, and let's look at this orange line. Let's look at our data. And as it keeps getting further and further down the line, we're going to be at 20. So our line here levels off at 20. But notice it never gets below 20. So we're going to have an asymptote, which means that we get closer and closer and closer to 20, but it's never actually going to cross 20. And here we cross here at 85. And so think about it for a second. When x is 0, we're going to have 1.9 to the power of 0, which gives us 1. And then we're just left with 65 plus 20, which gives us 85. Okay, so I want you to try to answer the next questions on your own. And I'm going to put up the answers in just a second. Okay, so how did we find the initial temperature? We plugged in 0 in for x. Now add the line x equals 4. What does the intersection of these two lines represent? So if I draw the line x equals 4, we get this intersection here. This intersection represents the temperature of the coffee when the time is equal to 4 minutes. Okay, add the line y equals 50. What does this intersection of the two lines represent? So this intersection of the line y equals 50 is going to say how long is it going to take for the temperature to get down to 50. Okay, because this x-axis is time and the y-axis is temperature. Okay. Question 5. What does the intersection of the two graphs represent? So the intersection of the graphs represent what the time is going to be for the coffee to be at a particular temperature. Okay, and what is the equation of the horizontal asymptote? So as we can see here, our equation of the horizontal asymptote is y equals 20. Okay, and let's write that up here too. Y equals 20. Okay, and this represents, I would say this represents the air temperature, because the coffee is not going to get colder than the temperature of the air. And I will do the rest of the handout on another video.